In 1993, I was 10 years old and I went with my family to see the movie Jurassic Park. It played at the Shulman Six Theater in Bryan, Texas. I remember it like it was yesterday, in part because it's my favorite movie of all time. And why is that? Because it's the best movie of all time. It's got everything, it's got dinosaurs and people. Did I mention it has dinosaurs? And it really just captures like the imagination. Sidebar, I just read Jurassic Park for the first time. And you know, 30 years later, it does leave a little bit to be desired from the biochemist perspective. I don't think that I saw the word genome mentioned a single time. The DNA discussion is all kind of smoke and mirrors. But with that said, that was the first time I ever heard the term DNA. And in particular, I heard it because there's an animation in the movie that includes a cartoony character that says, Dino DNA. And I just love that. About once a month, the phrase Dino DNA with that particular tone comes to my brain. Now, today, we're not going to be talking any more about Jurassic Park, but instead, we'll be talking about nucleic acids. Now, nucleic acids, we're going to be talking about them with respect to, oh, got ahead of myself. We're going to be talking about them with respect to their building blocks and their parts. For starters, DNA and RNA both have a sugar. Ribonucleotides include the pentose sugar ribose. So, a cyclic form of ribose. Ribose is a ketose, it's a 5-carbon sugar. You'll learn more about that whenever we talk about sugars. In deoxyribonucleotides, we have a sugar that is known as deoxyribose. Now, which one of these do you think lacks an oxygen that the other one has? I'll give you a second. You're right, deoxyribose. Now, here are our two sugars. I'm going to scribble this out because what I want you to focus in on is the sugars rather than the entire structure. We've got a ribose and deoxyribose. Well, deoxyribose at this position right here lacks an oxygen that ribose has. So deoxyribonucleotides and ribonucleotides, the only difference between them is, or the predominant difference between them is at the sugar level. Does it have an oxygen or does it lack an oxygen? With that in mind, between these two sugars, and looking specifically at that position, is one of them going to be better at hydrogen bonding than the other? Yes. Ribose is better at hydrogen bonding than deoxyribose because it has this hydroxide group. That hydroxide group is going to be fantastic at hydrogen bonding. In that same position with a single hydrogen, it's not going to be as good at hydrogen bonding. Why is that? Because this atom right here is a carbon. It's not something nice and electronegative like an oxygen or a nitrogen. So ribonucleotides and ribose, they're better at hydrogen bonding than deoxyribonucleotides. Now, this term nucleotide, so this versus nucleoside. I want you to be familiar with those terms and be able to distinguish between them. A nucleotide consists of three different things. A nitrogenous base. This is the thing that you're probably most familiar with respect to DNA and RNA. These are our base pairs, our nitrogenous bases. This is your A, T, G, C, U, adenine, thymine, guanine, cytosine, uracil. Those nitrogenous bases are found right here. A nucleotide also has a sugar. We've already talked about that. So, with that said, there's a deoxyribonucleotide and a ribonucleotide. If we look at this molecule right here, I can tell you that this is the makings of an RNA molecule. Why is that? Because this position right here, we've got that oxygen. That oxygen at that 2' position indicates we're dealing with an RNA molecule or a ribonucleotide. Then the third part of a nucleotide is to have a phosphate, at least one phosphate. Now, this phosphate right here off of this carbon is known as the alpha, alpha phosphate. A nucleoside, by comparison, only has a sugar and a base. It does not have a phosphate. I always think of nucleotide. For some reason, my mind goes to phosphate. I hear phosphate. I hear nucleotide. Those hard T's kind of make me think about one another. They're part and parcel, they're one and the same. Okay, our nucleotides. We've got this right here, ribonucleotides and deoxyribonucleotides. Like I said, we've got our alpha phosphate, we've also got a beta and a gamma. There's three phosphates. That would be an example of a nucleotide triphosphate. If there's only two phosphates, so only the alpha and the beta, that's a nucleotide diphosphate. An NMP, a nucleotide monophosphate. So NMP, NDP, and NTP are nucleotide mono, di, and triphosphates. Now, with that said, the other component of a nucleotide is the nitrogenous base. We've got a total of four different nitrogenous bases that can be in this place. They are adenine, guanine, cytosine, and uracil. These are the four nitrogenous bases that can make up a RNA molecule. Now, if we look down at our deoxyribonucleosides or ribonucleotides, we'd see adenine, guanine, cytosine, thymine. Okay, the difference between these two is uracil is found in an RNA molecule, whereas thymine takes its place in a DNA molecule. Now, that deoxy is pretty significant because we want to indicate that is a differentiator between these molecules. Ribonucleoside versus a deoxyribonucleoside. We use the terms AMP, ADP, and ATP for adenine monophosphate, adenine diphosphate, and adenine triphosphate. We use DAMP for adenine or adenine monophosphate when we're talking about the deoxy form of it. So we would say deoxyadenine monophosphate, deoxyadenine diphosphate, or deoxyadenine triphosphate. So if anyone ever talks to you about, oh yeah, you got to get a bunch of ATP, they might unknowingly be talking about, well, one of the building blocks for RNA as opposed to DNA. ATP is different from DATP. DATP indicates that we do not have an oxygen right here. So when we see this right here, we are talking about a ribonucleoside because of the fact or because of the presence of that hydroxide group there. Now for our nitrogenous bases. These nitrogenous bases are found in two different classes, pyrimidines and purines. The purines are either adenine or guanine. Your pyrimidines, there are three of them, cytosine, thymine, and uracil. We talk about thymine and uracil as being kind of substitutes for one another because they both are pyrimidines. They take the place of one another in an RNA or a DNA molecule, respectively. Now, when it comes to your nitrogenous bases, I want you to be able to recognize these. Now, what makes this a little bit, or what can make this a little bit more complicated, is the fact that the atoms within these rings are numbered, and it's easy to number them and keep track of them. Whenever you're looking at a purine, your numbering starts, I always like to think about this as it's counterclockwise. I'm going to start in the upper left-hand corner. So this nitrogen is atom number 1, 2, 3, 4, 5, 6. And then I'm going to go clockwise to finish up my other ring, 7, 8, and 9. Same thing for guanine. We're going counterclockwise, 3, 4, 5, 6. Then finish off this other ring, 7, 8, and 9. When it comes to pyrimidines, we start at the bottom, just like pop superstar Drake. 1, 1, 1. We're starting at the bottom, but then we're going to go clockwise, 2, 3, 4, 5, and now we're here. Again, just like pop sensation Drake. We're starting at the bottom, and now we're here. Bottom, and now we're here. Okay, so We have six atoms that make up our pyrimidine ring. We have nine atoms that make up our purine rings. One of the things that I've always remembered is that, or that's like a little mnemonic or a learning tool for me, is purines, shorter word, larger molecule. Pyrimidines, longer name, and smaller molecules. What I want you to be able to do whenever you look at these is I want you to be able to identify. I want you to, if I gave you a structure, I'd want you to be able to say, aha, that's adenine, or aha, that's guanine. In addition to that, I would want you to maybe be able to, if I were to say, hey, we've got a guanine with a methylation at position number 7. I'd want you to look at that and be like, aha, that's what that looks like, as opposed to this right here. So if I gave you these two molecules and said, select which one of these has guanine methylated at position number 7, I'd want you to circle this one. Okay, now with that said, we went through the numbering, but what's helpful in addition to that is to be able to say, okay, well, how can I separate these two? How can I distinguish them from one another? One of the things that I do is I just pick out one thing, and maybe this is lazy. I hope that it's not. No, it's not lazy. I think it's pragmatic. It's practical. I pick out one thing and I say, okay, well, at position number 6 in my purine rings, what do I have? Well, adenine is where I've got an amino group. I remember at position number 6, amino, and I look at that and I say, aha, amino for adenine or adenine for an amino. So that's what I do. Then at position number 6, I can just differentiate it from the other. And I say, okay, well, I got a carbonyl oxygen. Is there something that is going to trigger me to say, aha, that's what that is? No. I know that I only have two purines. And if I can remember the structure of one, then by process of elimination, I know the other. For my pyrimidines, what I always do is I say, okay, well, at position number 2, they all have a carbonyl oxygen. So that doesn't really help me. But then if I look at, let's see, ooh, thymine. What I do is I say at position number 2, 3, 4, 5. At position number 5, I've got a methyl group. Okay, so position number 5, thymine has a methyl group. Uracil, well, uracil has a carbonyl at positions number 2 and at position number 4. And I use uracil and cytosine to kind of play off of one another. So the way that I work is I say, okay, I know the structure of thymine, methyl at position number 5. Uracil and cytosine, what makes those different from one another? Methyl, or sorry, is a um, amino group at position number 4. That's what helps me out whenever I'm looking at these structures. Now I'm going to take a gander. Okay, so that tackles all of our nitrogenous bases, nucleosides versus nucleotides. I'm going to touch on this nomenclature a little bit because this is important. It comes to linkages. If you look back at these structures right here, yeah, if you look at these structures right here, one of the things that I want you to notice, and this is significant, if we look at our numbers of our atoms within our ring, and if you've ever learned anything about DNA or RNA, you talk about it being a 5 prime to 3 prime direction. Well, this is 1 prime. That prime indicates, or that prime is unique numbering for the ring of that sugar. So that is the one prime atom. If we jump over here and we look at our nitrogenous bases, we do not use the prime numbering scheme. What that allows us to do is to look at the linkage between, say, a nitrogenous base and a ribose ring and say, okay, well, what is the linkage here? Well, this is a 1 prime to 9 linkage. So I'm able to use numbers to identify my atoms, and the numbers are not reused because this is atom number 1, this is atom 1 prime. So our prime numbering, anytime you see a prime number, or sorry, a number with a prime by it, that's in reference to the sugars. Non-primed numbers, for example, 2, refers to the base, the nitrogenous base. The phosphate group may be attached to the sugar at either of two positions, and chances are that's going to be at the C3 prime. And if it is there, that is a C3 nucleotide or a 3 prime nucleotide. If that phosphate is attached to the 5 prime, it is a 5 prime nucleotide. So here's just kind of a depiction of all of the different sugars that we talked about. We've got AMP. Well, this is adenine. And I know that this is not, or this is a ribose because it's AMP as opposed to DMP. This is a nucleotide because I've got a phosphate there. Now, the full name for this nucleotide is adenylate, adenosine 5' monophosphate. It's pretty customary to use the nucleoside names, which are adenosine, guanosine, uridine, cytidine, and then say the number of and then say the placement of the phosphate and the number. So if I said deoxyadenosine, that term deoxyadenosine is not a phosphorylated molecule. There's no phosphate there. But if I add to that deoxyadenosine 3' triphosphate, what does that mean? Okay, deoxy, that means I'm dealing with a DNA molecule. So at the 2' position, I do not have an oxygen. My nitrogenous base is adenine. 3', okay, so that would be, okay, this is my 3' carbon triphosphate. That means I've got OPO, that's 1, PO, that's 2, PO, that's 3. So that's my 3' triphosphate. So this just kind of catalogs all the different variations of them. Notations and shorthands that you should be familiar with is what's A mean? What's AMP? What's ATP? What does DG or what does DGMP mean? What does DGDP and what does DGTP mean? When it comes to phosphate, or sorry, when it comes to nucleotides, I have never seen a tetraphosphate. And I think it's because that fourth phosphate would simply be unstable. Remember our phosphate identifiers, alpha, beta, and gamma. Those are our 3 phosphates, and that's what constitutes a nucleotide. Here's just kind of another continuation of that. I'm not going to ask you the names of the nucleotides, but they do have unique names. Adenylic acid, guanylic acid, cytidilic acid, uridylic acid, deoxythymidilic acid. I'm not going to ask you those names because the convention is to follow the nucleoside plus place the phosphate and identify the number of them. With that said, there are some derivatives of or some slight variations. If you look at this molecule, these are all nucleotides. They're all nucleotides because we've got a base. We've also got a phosphate. So these are all nucleotides because we've got a base, a phosphate, and a sugar. Now, with that said, what do we have to think about these? Well, if we start in the upper left-hand corner, this is adenosine. That's the name of our nucleoside, 5' monophosphate. If we go to the next one, adenosine, 2' monophosphate. Lower left, adenosine, 3' monophosphate. And lower right, adenosine, 2', 3' cyclic monophosphate. This is a molecule in the lower right-hand corner that you might be a little bit familiar with because maybe you've talked about or taken another class where you talk about secondary messengers and cyclic AMP, commonly known as CAMP. Cyclic adenosine monophosphate is a nucleotide and it's involved in lots of different signaling mechanisms within your body. Okay, so that's our Last item here is this is really just kind of an introduction to show you that there's lots and lots of different places that you might find a nucleoside. Here's a nucleoside as a part of a molecule known as coenzyme A. Here's a nucleoside as a part of a molecule known as nicotinamide adenine dinucleotide. Then here's our last nucleoside as a part of flavin adenine dinucleotide. These play different roles as like electron carriers, as high energy compounds involved in metabolism. The ones that I want you to be familiar with is this NAD plus. That's N, not M. NAD plus, because of the fact that NAD plus interconverts or undergoes redox reactions between NAD plus and NADH. Um, So there's lots of electron transport that NAD plus and NADH are involved in. And these, at the end of the day, are nucleotides. And I think that's all. Yeah, there we go. Um, with that, I hope this is helpful. I hope you got a good understanding of the nomenclature, and I'll see you in the next